Hello, everyone, and welcome to the final live stream of Chemistry 223 for this summer. My name is Travis. I'll be working you through this live stream as always. Today, we're going to talk about types of radiation and radioactive decay, and also go into half-life equations and stuff like that. To get started with, as always, I'm going to paste a few useful links in the chat window. So there's a link to the Learning Center's webpage, as well as links to their Facebook and Instagram. So follow them on Facebook and Instagram so we can see updates whenever we have new resources available, such as these live streams, which we just started this last year. I'm also going to post a link to the PSU or the Learning Center's YouTube channel, specifically this playlist for Chemistry 223. There's also playlists up there for Chem 221 and Chem 222 if you have to do any reviews as well, plus other subjects we've covered in the past. So definitely check those out. Give them some bookmarks and likes if you like the videos on there. So let's go ahead and get started. We're going to start out with just the idea of isotopes, and for this question, for the following isotopes that have missing information, we want to fill in that missing information. So whatever is an X, we want to fill in that missing information. Most of this is pretty straightforward once you know the format of things. The X kind of determines which atom it is. It's just the label that we give those atoms. The Z number down on the bottom left corner, that represents how many protons the atom has. And then the A number up at the top left corner is giving you the combination of protons and neutrons, which is the nucleons, basically all the different particles in the nucleus itself. And different isotopes are going to have different values of A, so different values of nucleons, but it could have the same number of protons. So, for example, carbon 13 versus carbon 12, they both have 6 protons, which is how many protons carbon has, but they have different numbers of neutrons in there. So for carbon 12, you're going to have 6 neutrons as well. For carbon 13, you're going to have 7 neutrons. But they're acting as the same atom, essentially. So let's get started. For part A here, it says we have 34 nucleons and 14 protons. And we want to know what X is. X is going to be then, if we look at our periodic table, we look at what 14 is here, and we can see that silicon has 14 protons in the nucleus. So that's going to be silicon. So I'll write Si. Most of these are pretty straightforward once you get the hang of it. It's just kind of figuring out what's what and making sure that you know what's going on, because going forward we're going to use these numbers in a lot of different ways when we talk about decay. So for part B, we have 36 nucleons, and we know it's phosphorus, P. So if you go on our periodic table, well, phosphorus just happens to be the next one up on the periodic table, which is 15. So 15 would be the number of protons in the nucleus. I was making them red for the unknowns. Let's do that. For part C, I'm going to go over here. We have 57 nucleons, and we have X and Mn. So Mn, if we find on our periodic table, it's right there in the middle, manganese, and you see its atomic number 25, which means it has 25 protons in the nucleus. 25. Part D, it's 121, 56. Well, we don't know what the symbol for it is, what that element is. So that 56 tells us everything we really need to know in that regard. Just looking at 56, you can see that's barium. Barium's number 56 represented by Ba. And we have solved for problem 3. Like I said, it's pretty straightforward once you get the idea of it and what's going on. We're going to go forward and talk about radioactive decay next. So these are all the different types of radioactive decay that they're out there. There's alpha decays, beta decays, gamma decays, positron emissions, and electron captures. Those are the 5 different types we're going to be working on here. Looking at kind of what's happening for each of these. For alpha decay, alpha is really this helium atom. That's what we call an alpha particle. So helium has 2 protons and 4 nucleons total. So 2 neutrons, 2 protons. That's helium. So what happens when we have alpha decay is we have this cluster of 2 protons and 2 neutrons in the nucleus of some atom, and they get excited enough where that whole cluster leaves, and it's kind of just bounces from the nucleus, and we're left with this lack of nucleons there. Everything kind of reorders, so it's still a compact nucleus, but our new nucleus is going to be shy 2 protons and 2 neutrons from what the original was. That's what they're kind of saying here, is whatever that product is A minus 4 and Z minus 2. But that's basically a helium atom exiting the nucleus of the atom and decaying out. For beta decay, beta is just a fancy word for an electron, essentially. And we have electrons, which are negatively charged. They have no neutrons or protons in there. We represent it with that by that -1 and 0 up at the top. It always has that little lowercase e. But when we have beta decay, what's happening is a neutron is basically losing an electron. And so it starts out neutral, and then it loses a negative charge, making it more positive. So the neutron sheds that negative charge, becomes a proton. So in that process, we get that Z plus 1. So the number of protons are increasing in that by 1 because a neutron is turning into a proton. Notice that the nucleons, the A value, is the same value. It doesn't change in value because we have the same combination of neutrons and protons. It's just a neutron is turning into a proton. For gamma decay is essentially when that whole nucleus is at some type of excited state. It could be there's a little bit of extra energy stored in there from the spin of the protons and neutrons or something to that effect. And when it relaxes, it releases that energy. And it releases that in the form of a highly energetic gamma radiation. So really, this is just a really energetic light wave. So there's really, the only change is it goes from an excited state to a non-excited state. There's no change in the atomic structure, really, that's going on. The A and Z values are the same, and the element's going to stay the same element. For positron emission, positrons are just like electrons, except for being positively charged instead of negatively charged. Positron is the antimatter of an electron, essentially. It has the same mass and just the opposite charge, same magnitude of charge, just a positive instead of a negative. So the same type of deal is happening, but instead of Z plus 1, we're getting a Z minus 1. And here we had a neutron turning into a proton. Now we have a proton turning into a neutron as that proton loses its positive charge. For the electron capture, here we're taking an element and we're basically, it would be like if you bombarded it with electrons. And an electron finally hit the nucleus of it directly, and it hit a proton in there, and the proton plus the electron turns into a neutron that way. And when that happens, the deceleration of the electron will actually emit a gamma ray, or sorry, an X-ray, another highly energetic light wave. Not quite as energetic as gamma rays. X-rays are less energetic, but still, it's a lot of energy going on there. But just in this case, we have electron capture, so it's capturing that electron there. By capturing it, it's going to be on the reactant side, and the product is then going to have one less proton in it because that proton's turned into a neutron. The nucleons total have stayed the same. So those are the different types of nuclear decay we're going to be dealing with a lot here. And we're going to go through a couple different problems where we're just trying to balance this nuclear decay equation, such as this. So for number 13 here, I'm going to write it out, 27, 13. 13 is aluminum plus 4, 2 of helium. I don't know. I always write it as a fraction. I shouldn't do that. 4, 2 helium. So that's an alpha particle there, that helium atom. So here we're bombarding aluminum with helium atoms, and eventually they collide, and we get that alpha particle capture. And it's going to produce some element and a neutron. So we can see that's a neutron. There's no protons there. It's a lowercase n, but there's one nucleon up at the top, right? So in this case, all we really have to do is make sure that the values for A are balanced on both sides of the equation, and the values for Z are balanced on both sides of the equation. So A total say total, needs to equal 27 plus 4, which is 31. And Z total needs to equal 13 plus 2, which in this case is equal to 15. Was always equal to 15. So we can see that the right side of that equation needs to have a total of 31 and 15. But since we have one neutron here, we can subtract 1 from that and say that's 30 and 15. That's going to be the element that this decays down into. So now we have to figure out what is an element that has 15 protons. So jumping back over, and we talked about it earlier, it's phosphorus. Looking up the 15th element on the periodic table, we see that phosphorus has 15 protons. So write a big P there, and we can see that now our equation is balanced, and we found what aluminum will decay down into when it captures an alpha particle. For part B, we have 239, that's plutonium. 239, which has 94 protons in its nucleus, and we're adding something to that. It's going to capture something to create 242 Cm, 96 plus 1 neutron. So looking at the periodic table again, see plutonium, plutonium is down here, number 94, and we can see that curium is Cm, and that has 96. And that's what we had there. So again, adding these together, we can see plutonium had 94 and curium is going to have 96. So we must be adding something with 2 protons to it. So you can already guess what that's probably going to be, and we can verify that. So we think it's going to be an alpha particle. Now 239 plus 4 is 243. But we're going to lose one of those as a neutron to make it 242, and that's it. So we see we just did the math there to find out the difference between those two sides to fill in what that atomic number is and the number of nucleons, and then identified what element has that. And helium has 2 protons. For part C, we have nitrogen 14. We're going to add to that an alpha particle, or helium, and that is going to give us something plus a hydrogen. Okay, basically this is a proton, right? A hydrogen, the standard hydrogen atom is really just a proton with no neutrons and electrons around it. If you strip that, or a single electron, if you strip that electron away, it becomes H+, which we've talked about a lot in acid-base chemistry. But in this case, we really just want to know what this is going to be. So 7 plus 2 is equal to 9, and 9 minus 1 is equal to 8. So now you have 8. Oops, let's stick with red. 8 on the proton side. 14 plus 4 is 18, minus 1 is 17. And then element with 8, I believe, is oxygen. So what they're doing is they're taking nitrogen, they're bombarding it with alpha particles and creating oxygen. And since they have an extra proton there, they create oxygen and hydrogen by doing that. Part D is uranium 235 is going to produce something plus 135, put 6, 55, I think that's cesium, plus 4 neutrons. So that's interesting. There's 4 extra neutrons flying out of here as well. So we can add up all of these as well. We have on the bottom 92 minus 55. I'm going to pull up my calculator for this just to make sure I don't make a mistake. 92 minus 55 is equal to 37. So I know there has to be 37 protons there. And if we have 235 minus 135 minus 4, because there's 4 different neutrons, each neutron having one neutron in it. That's 96. So then looking for, it was 37. Boop, boop, boop. There we are. Rubidium. It's 37. So I can fill that in there. So that's the basic idea of how we can see what's going to happen if we see what some of these are. Well, then the extra element must be, in this case, rubidium 96. Same idea here for part number 14. We'll run through this real quick. 7,3 lithium, so lithium 7, plus some mystery element is going to produce 2 helium atoms. So 2 alpha particles are produced by this decay. This capture, really, because it's capturing whatever this element is and creating 2 helium atoms. So we can see right away that 2 times 4 is 8, minus 7, so that has to be a 1 up on the top. 2 times 2 is 4, and we have a 3 for lithium, so that has to be a 1 there. Well, that's going to be a proton. I'm going to call it H, hydrogen. So lithium, if you bombard it with protons, will create helium atoms. For part B, 14,6 carbon, that's carbon 14. It's going to produce nitrogen 14 plus a mystery element. So we can see the 14s are the same in this case. So we end up with a minus 1 here, because 7 minus 1 equals 6. And we have to have that balance between the 2 different sides for Z and A. And then we have 0 up on the top. So the only thing that has a negative number down at the bottom is going to be an electron. Anytime you have a 0 at the top, you end up with either an electron or a positron. And depending on whether that Z number is positive or negative determines which one it is. Part C, 2713 aluminum again, plus an alpha particle. This is looking pretty familiar. It's going to produce 10N. We're just adding up these numbers. We have 15 here. And we kind of did the exact same thing for part A over there, didn't we? So we know this has got to be a 15. And this has to be a 30. And that's got to be a phosphorus. Just because, well, we did it right here. Part D, 250 and 96. Cm is going to produce, is that still curium? Yeah, curium is producing some element plus strontium 98, which is 38, plus 4 neutrons. So just doing the math, I have 250 on the left-hand side for my A value. I'm going to subtract from that 98, and then I'm going to subtract from that 4 for the 4 neutrons that I have. And that gives me 148. So 148 is my new A number for this mystery element. For the protons, I'm going to do 96 minus 38. And then since neutrons have no protons in it, I don't do anything there, and I have a 58. Hopping over to the periodic table, we can see 58 right there. Cerium, Ce. There we go. And now we have a balanced chemical equation for all of these balanced nuclear equations. So those are all pretty straightforward and simple once you realize kind of what's happening in there. It's really just adding and getting a balance of the A and Z values for either side, and then identifying what that element is based on your periodic table. So for these guys are kind of doing the same idea but in words, and we can see that it says the production of oxygen 17 from nitrogen 14 by alpha particle bombardment. So really, I'm just going to put this as, put the arrow there, and the word production means it's a product. So the production of oxygen 17 from nitrogen 14 by alpha particle. So alpha particle is 4, 2 helium. We know nitrogen is 7, oxygen must be 8. So now we want to write that and balance the equation. So if we just look at this, 7 plus 2 is 9, and oxygen's an 8, so we were missing something. So I'm going to put a 1 over there for whatever we're missing. 14 plus 4 is 18, minus 17 is another 1, and we were missing a proton. So that was part A. Part B is the production of carbon 14 by a nitrogen 14 by neutron bombardment. Now, a neutron bombardment would be this, adding a neutron to the reactant side. We're bombarding that nitrogen with neutrons. And nitrogen, of course, is element 7 on the periodic table, and carbon is element 6. And if you ever had doubt, jump back over to your periodic table and take a look at them. So now, doing the math on this one, we can see that we're missing something on the right-hand side because we have 7 on the Z and a 6 total on the right. So we need a 1 down there at the bottom. Looking at the top, we have a 14 and a 1. So we need a 14 and another 1. So hey, we have more hydrogen going on there. For part C, we have the production of, let's say that's 233. That's TH, which I believe is thallium or thorium. My mistake. Thallium's TL. So, and that's 90. That's what the information we really needed there. From thorium by neutron bombardment. So you see the difference is I have 232 thorium, and I'm bombarding it with a neutron to create 233 thorium. Now when I add these sides up, I see that they're already balanced. I have 232 plus 1 is 233, and 90 plus 0 is still 90. So we're done there. That's good. For part D, the production of uranium-239 from uranium-238 by, and notice this type of bombardment, that hydrogen has an extra neutron. We call it deuterium. It's basically heavy hydrogen. The hydrogen is the same as it has before, one with 1 proton, but now it has a neutron floating around in there as well. Not really floating, it's bonded into the nucleus. But it's a little heavier. When these collide, they eventually make helium, which is how the sun makes energy, essentially. So we can add these up here, and 238 plus 2 is 240. So we know we have to be having 1 more over on the right side. And then uranium is going to produce uranium. So whatever the Z value for uranium, 92, it's going to stay the same on both of these. So we must have that extra 1. So it really just steals a neutron from that deuterium in that nuclear reaction. So looking over it, now we're going to get to something a little bit more complicated. Here we have the decay of thorium down to lead. So we start out with thorium-90, or thorium-228 really, and we're going all the way to lead-208, and we want to show every step along the way after an alpha decay, alpha decay, alpha decay, alpha decay, beta decay, beta decay, alpha decay. So there's a lot of different decays going on there to get that. There's multiple steps basically to go down, and we can show what each of those are just by working it step by step. So I'm going to start off with 228-90 thorium. So I know this is it's gonna be a emission. It's not a decay. It's an emission of alpha particles. So this is going to emit an alpha particle. Really, I want to change these color-wise. And then when it emits an alpha particle, what's the remaining element that's there? Well, number-wise, we know 228 minus 4 is 224. and 90 minus 2 is 88. So now we just have to look on the periodic table. What's 88? 88 is radium. Radium. That's Ra. So then the next step is going to start out with that radium. And it's going to emit an alpha particle. And then what's left over from there? Number-wise, we're at down to 220 and 86. So looking over at the periodic table for 86, we're over here at radon. It's Rn. So again, starting the next step at radon. And so we've done 2. I'm going to cross them off when I'm done them, so I keep track of what's going on. 2 alpha decays. We're on a 3rd alpha decay now. That's going to be 216 and 82. So hopping over here, 82 is lead. I didn't do... That was -2. That was -2. This should have been -2. Should be 84. I was subtracting 2 from there instead. So 84 is not lead yet. We have polonium. Polonium. PO. So that's 1, 2, 3. One more. So that 216, 84. PO. Then is going to make or decay, emitting to another alpha particle, which will give us 212 and 82. So 82 was lead. So now we're down to lead, which is what we were looking for. But we wanted lead 208. We have lead 212. And we're not also done. We have to emit 2 beta particles and an alpha particle again. So let's see what happens when we do that. 212, 82. Lead is going to emit a beta particle, which is an electron, plus what? Well, at this point, this goes back up to 83, 212. 83 is bismuth. And then 212, 83 bismuth. So bismuth 212 is going to emit another beta particle. And then be back up to 212, 84, which is PO. But really the difference between these two and those steps is we have the same number of protons but less neutrons there. So it kind of had to drop back down and then it dropped back up. And now it's going to go into another alpha particle decay. So this is going to be starting 212, 84, be an alpha particle decay here to make 208, 82 PB. And you can see every step along the way, I did alpha decay or alpha emission, alpha emission, alpha emission, alpha emission, beta, beta, and then alpha. And we can see how the path that it takes to get from this to this. Number 34 here, the isotope, this is thallium, TL208, undergoes beta decay with a half-life of 3.1 minutes. So now we're getting to these half-life formulas. And I'll write out this equation real quick. I guess I want to know what isotope is produced by that decay. So if we start out with 208, 81, which is thallium. Write my L's like this so I know it's an L. is going to produce, and it says beta decay, so it's producing an electron, plus, this must be 82,208, which is lead. And we just looked at that on the last problem, lead 208. So you see, this is actually decaying up the periodic table to lead, where the last time it was decaying down the periodic table to lead. We started with a different element, of course. So what isotope is produced, we have lead 208. So that's part A. For part B, how long will it take for 99% of the sample of a pure thallium 208 to decay? So for this, we need to use the wonderful half-life formula, or decay formula, which I write out like this usually. Other people do too, but there's different versions of it, different forms. You can rearrange it. I focus on this version and then I rearrange it as needed. So in this, that N of T is equal to the number of particles at time T. So whatever time T is passed, this tells us how many particles are left after some time of T is passed. In naught is the initial number of particles. So usually you have like a final and an initial. In this case, NT is your final, N naught is your initial, and you can figure out the difference between those there. Of course, lambda is going to be what we call decay constant, which is really like a decay rate. It's how fast it's decaying. We can tweak that number a little bit. Every element is going to have basically a different decay rate, and based on the decay rate, it tells you how fast or how slow it decays. And T is time. So whenever you're doing this equation, you want to make sure that whatever the decay constant is, it's usually a per some time, just so we can multiply it by time and get something unitless for our exponential. So in this equation, using this equation, if we're looking for 99% of it, we can rearrange this just by dividing by this N naught on both sides. And we get NT over N naught is equal to e to the power negative lambda T. And that fraction is basically a fraction of the original. NT is how much is left divided by how much was there initially. And we can turn that fraction, which will always be less than 1, into a percentage. So in this case, I want to say how long will it take for 99% of the sample to decay. So we're not looking for 99% there because we want to see how much after 99% is gone. We want to look at for 1%. But first, to do that, because ultimately this needs to equal 0.01. That's what we're really shooting for there. But to solve for that equation, we need to know the lambda value, the decay constant, and the time. Well, and what they're asking is how long it will take. So they want us to solve for time. So first we have to find what the decay rate is. And to do that, we would have to find its half-life. Now it tells us the half-life up here. So the half-life is when this ratio, NT over N naught, is equal to 1/2. And of course, that's still equal to e to the negative lambda T. So if that ratio is there and we know what T is going to be, we can then solve this for lambda. So let's do that. If I take the natural log of both sides, so natural log of 1/2 is going to be equal to, and the natural log of e to the power of negative lambda T is just going to be equal to negative lambda T, which is why I take the natural log. And we can go through the derivation of why that is, but definitely refresh on the logarithms. I'll do it real quick. So if I do the natural log of e to the power of negative lambda T, basically rules of logarithms now say I can pull down that exponent and put it up front, which is equal to then negative lambda T ln of e. This becomes, not 0, but 1. And we have this is equal to the lambda T. So to rearrange this now and solve for lambda, I'll end up with the natural log of 1/2 divided by negative time. It's going to equal my decay constant. So it's a quick rearranging of this basic formula up here to tell me what my half-life is, or using the half-life time, I can find what that decay constant is. So now plugging in values for that, the natural log of 1/2 divided by 3.1 minutes will be a negative, because that's what it told me the half-life was. 3.1 minutes is going to be equal to lambda. My calculator will tell me that negative natural log 0.5 divided by 3.1 is equal to 0.22. That'd be a per minute, because that minute's in the denominator there. So now that I have my lambda value, put a little box around that, I can use this equation and say that 0.01 is going to be equal to e to the negative 0.22 per minute times t. And now I just have to solve for t. So solving for t, again, is the same idea. We use the logarithm, so I take the natural log 0.01, which will equal negative 0.22 per minute times t. Can then divide, get the natural log 0.01 divided by negative 0.22 per minute to equal, there we are. So the natural log 0.01, so that's 1% essentially. That's why we were looking for after 99% decayed, divided by negative 0.22. Well, really, let's skip the rounding error and just grab that value. And that is going to be 21 minutes. Round to 2 sig fig, because they gave me 2 sig figs here. So think about 21 minutes, which is how long it would take for 99% of that sample to fully decay. Part C, what percentage of the sample of pure thallium remains undecayed after 1 hour? So now that we have that decay rate, a lot of these are really simple, because we have NT over N naught, which is that fraction that we have. Here they're asking for a percentage, but we can deal with that. It's equal to e to the power of negative 0.22 divided, or per minute, times 1 hour, which is really 60 minutes. Zoom in a little bit there. So just plugging in the values that we have for that now, we can see what this is going to end up being. So it's going to be my exponential, e to the power of negative, that was my decay rate there, times 60. And that equals 1.5 times 10 to the negative 6. So that's not a percentage yet. I need to multiply by 100 to get a percent. So that's really 1.5 times 10 to the negative 4%. And that would be part C. The next question here, next problem, is we have the isotope strontium-90. It's one of the extremely hazardous species in the residues from nuclear power generation. The strontium in 0.5 grams samples diminishes to 0.393 grams in 10 years. Calculate the half-life. So they're telling us the initial mass of strontium and then the final mass of the strontium and how long it diminishes to in 10 years, or how much it diminishes into in 10 years. So we can utilize that using our equation, N over T, or NT divided by N naught. I'm going to write it like that because we're looking for that fraction, right? Oh, they want us to calculate the half-life. But we can use this fraction, e then to the negative lambda t, because we don't know what lambda is yet. And we need that to solve for the half-life. But we can utilize this equation here. So the initial value is going to be 0.5 grams. And that's supposed to be the number of particles in there. But since we're using the same element on both of them, they have the same atomic mass. So we can turn that grams into moles and turn that moles into atoms. But at the end of the day, we're going to do the same process to turn the mass here into moles and into atoms as well. So if we did that to both of them, it ends up being the same ratio. So as long as we're taking a ratio of two values and they're the same basic units, we have that same amount, essentially. So we can utilize those values directly. And then just solve for our decay constant. To do that, I can say the natural log nt over n naught is going to be equal to negative lambda t divided by negative t and that will equal lambda. So now I know I have my values t here, nt, and n naught there. So I have everything I need to solve for that at this point. So plugging those in, taking the natural log of nt 0.393 divided by 0.500. That value inside that logarithm should always be a fraction, should never be greater than 1. If it is, you probably have it arranged the wrong way. So take a look at it. Divided by negative time is 10.0 years. And that's going to equal my decay constant. Take the natural log of those values, 0.393, divided by 0.5. And we are going to then divide that by a negative 10. And that equals 240.8. Say 240. I guess 3. So 241. 3 sig figs. Well, where'd it go? So that's my decay constant. I can then use that to calculate the half-life for things. Or this should be per year. Per year. I can use that to calculate my half-life now. To do that, I just go back to this original equation that I had, and I want to solve for time now. So really, I can take this one, since we're already at that stage, and I can flip it around a little bit. But in this case, this ratio, it needs to be 1/2. That's why it's a half-life, because the fraction that you have is half of that element has already decayed into whatever it's decaying into. So then we need to divide that by negative lambda. So in this case, that's and that would equal the time. So the natural log of 0.5 divided by negative 241, and that's equal to, time is going to equal to 0.0029 years. So that's the half-life then of what we got. And we can figure out what that is in months or hours or minutes. It didn't ask us anything specific, so I'm just going to leave it right at that. Number 39. So this is asking us to do a few different things. We have a sample of a rock, which was found to contain 8.23 milligrams of rubidium-87 and 0.47 milligrams of strontium-87. So we want to calculate the age of the rock if the half-life of the decay of rubidium by beta emission is 4.7 times 10 to the 10 years. So we can look at the equation. What's happening here? We have rubidium, that's Rb, which is number 37, is decaying by beta emission to strontium-87, which is 38. So that's the basic equation of what's happening there. And we have to see, in this first question, they tell us the half-life. They want to find the age of that rock. So to do that, using our equation, Nt over N naught needs to equal 1/2, which is equal to e to the negative lambda t. And that way we can find the half-life of the decay. So we know what that half-life is, so we want to solve for lambda. So if I take the natural log of 1/2, which will equal negative lambda t, that means that the natural log of 1/2 is going to equal, or 1/2 divided by negative t is equal to lambda. Plugging in that value for t, which was 4.7 times 10 to the 10, divided by negative 4.7 times 10 to the 10th power in years, I can have divided by negative 4.7 e to the 10. That's equal to 1.5 times 10 to the negative 11 per year, which is equal to lambda. Now that I have lambda, we want to find the age of that rock. So what we need to do is find out, based on these numbers, how old that rock is. So to do that, we know that the ratio Nt over N naught needs to be equal to, well, the amount that's there initially, we don't know. Or we do know that's going to be this amount plus this amount, because all that strontium was created through that beta decay of rubidium. So 8.23 milligrams plus 0.47 milligrams divided by 8.23 milligrams, because that's how much rubidium is left in there. That's how much is remaining still, essentially. So you have the remaining amount divided by the initial amount, which needs to equal then e to the negative lambda t. And we know what lambda is, so I'll put that in here, 1.5 times 10 to the negative 11 times t. So I'm going to find out what this number is here real quick. Make writing it out a little easier. Oops, I forgot my decimal. So this is going to be 0.95. Oh, 946, let's say. 3 sig figs. And the units of milligrams are going to cancel out along across the board. There we go. So now that we have that, we can take the natural log of each side. The natural log 0.946 is going to equal negative 1.5 times 10 to the negative 11 times time. We're going to divide by that decay constant. That equals time. Plugging that into our calculator, 0.946. Well, let's take the natural log of that number. Divide that by a negative 1.5, 10 to the 11, which is that. Gives us 3.76 times 10 to the 9 years. That was a per year thing. So that's the age that it is based off of the amount of rubidium that's left that has not decayed yet. That's assuming that all the strontium in that sample came from that decay of rubidium. The last part on here, back up. If some of the strontium-87, oh, I should make a note. Part of the reason I was able to do this simple ratio, even though I had two different elements, is rubidium and strontium, they're both the same atomic mass. Since I have a rubidium-87 and strontium-87, really there's a very slight difference. There's one proton in strontium that is a neutron in rubidium, but since the difference in mass is so negligible, they essentially have the same atomic mass. And if you look it up on the internet, what is the atomic mass of rubidium-87, you'll see that it's a 86.909. And if you look up what is the atomic mass of strontium-87, it's 86.909. So those are all grams per mole. We can't use the values on the periodic table for these. No, where is that there? We can't use these values on the periodic table because these are averages of all the isotopes. So those are taking all the different isotopes for them and multiplying it by their percentage of abundance. We get these numbers, which are about average, and that's relative to our region. If you go to a different part in space, they're going to have different concentrations of rubidium-87 per chance. So really, but if you're talking about a specific isotope, we can't use these. We have to use the mass of that specific isotope, because those, now we're talking about a very particular isotope. And in this case, those two isotopes of rubidium-87 and strontium-87 have almost an exact same mass, which is why I was able to do that ratio without having to convert them all to particles. So to answer this question now, if some of the strontium-87 was initially present on the rock, would the rock be younger, older, or the same age as the age calculated in part A? So if I were to look at this number here, so this is what we calculated, right? 3.76 times 10 to the 9 years. That's like 3.76 billion years or something ridiculous, right? They want to know if some of this, 0.47 milligrams of strontium existed in there already. How does that change our estimate of the age? Are we over? Are we younger? Or so on. So really what we're looking at is this number here, right? If this number is going to go down, because that number in our equation was how much of that rubidium had already turned into strontium. So we detected 0.47 milligrams of strontium in the rock, but some of that strontium was already there, which means it didn't come from our rubidium. This number on the top, that's how much of rubidium we detect is still in there. So that stays the same. So this number stays the same, and really this number is going down. And since that's on the bottom of our fraction, that means that this fraction as a whole is going to get larger. It's going to be a bigger number, right? Which is going to mean that this is basically an older rock. The age is going to be, their projected age is going to go up if we knew there was a certain amount of strontium in there already, strontium-87 specifically. And we could also see that since the graph of this would be an exponential decay, which looks something, can't draw that right. It would cross there, but it wouldn't cross there. Something along those lines, depending on your rate of decay, where it has a steep slope going down. Still don't like it. There we go. That's better. and this would decay off into nothing eventually. If we calculated out that we are here, and really there's less of that decay that's happened, we're really up here, and this axis is time. I don't know if that's explaining it well, but really we're farther to the left on that graph than we thought we were, because there's less of a decay that's happened already. So that's the answer to part B, at least my ramblings on that answer to part B. Think about it, and you can see it mathematically on how that would work. And it would also make sense that if some of that strontium we detected wasn't from radioactive decay, and we're basing that H on radioactive decay, less of that rubidium has decayed, therefore less time has passed. Last problem for me. This is a pretty quick one because it just says to write a balanced equation for each of the following nuclear reactions. We basically have already done a lot of these already, and here they're just wording it out. I'm not sure why it's so far in the homework. This is number 46. We did something similar. But for part A, we have mercury 180. So that's 180 mercury decays into platinum 176. And I could already see from the difference in the nucleons that there are 4 differences there. We can look at from platinum to mercury, the difference is 2, from 80 to 78. So this tells me it's probably a helium decay. For part B, zirconium, which is zirconium and an electron. So that's Zr and an electron are produced by the decay of an unstable nucleus. So something's radioactive and it's producing zirconium and electron. So hopping over here to find zirconium on our periodic table, can never find these quickly, which is always a pain because it's, I found it earlier. Oh, it's number, there it is. I was looking way off. Number 40 on the periodic table, the zirconium. I was looking for the atomic mass 90. It's throwing me off. So in this case, we have zirconium 90. And now we can just add those kind of backwards and know that this is going to be 39, 90, and then hop over 1 to uridium. For part C, we have thorium 232. I think that, yeah, is going to decay and produce an alpha particle and a radium 228 nucleus. So radium's are A, and radium is number 88. So just making sure, I should look at thorium TH, which is down here, number 90. Making sure everything adds up. The Z numbers add up. 90 is equal to 88 plus 2. And the A numbers also add up, so that's good. We don't have to add anything special to that. Last one, D, we have neon 19, which I think has 10 because it's right at the end of row 3, row 2, row 2. Ah, there it is, neon. Is going to decay into fluorine 19. Fluorine is 1 off of that, so that would be 9. So to keep this balanced, I need something with 1 and 0, and E, which must be that positive positron emission. So to recap, this is a positron. emission. This is a alpha emission. 2 M's or 1 M, I don't know. This is a beta emission. And this is a alpha emission. So they're emitting those particles out, and that's the end of my live stream today. If you have any questions, definitely go back on the videos and watch the videos. We have videos for pretty much every subject that's happened in 221, 222, 223. You can also schedule a tutoring appointment with our chemistry tutor this summer, Amir. He's great, and he'll be able to help you out with anything that you have trouble with. Best of luck for everyone that's been watching. Thank you for watching these videos, and enjoy yourself. Have a great day.